Okay, let's see what everybody did. Responses. A is the electrophile, B is nuclear. 35. Good. Okay, so that is indeed correct. Okay, so let's draw a little bit here. Okay, so remember, electrophiles are going to be electron poor, and so we will have on this molecule A, this is charged in this direction. So this carbon here is going to have the delta plus. The chlorine, of course, is the delta minus. Our nucleophile is going to have some lone pairs that it can use to attack with. And iodide has got exactly that. So if we were to connect the dots here, these electrons would attack this carbon, and that, because we're putting electron density into that sigma bond, we're breaking the carbon-chlorine bond. So those electrons are going to move on to the chlorine to become chloride, and this will be our leaving group over here. Now, this reaction is really interesting in the sense that the way that this reaction works is that sodium iodide is soluble in acetone. So it can solvate this. You've got sodium and iodine. They're both solvated by the molecule. So iodine's free to move around and attack stuff. But in acetone, sodium chloride precipitates out as a solid. So as soon as this chlorine leaves, it's going to form an ionic bond with the sodium, and it's going to precipitate out of the reaction as a solid. And so that's going to help drive the reaction to completion. So yeah, this is an interesting reaction because we'll see later on that iodine itself is a good leaving group. Iodide is a good leaving group. So this is a way to overcome that by using a specific solvent to make chlorine insoluble, and it crashes out of the solution. But the key point to this was that indeed iodide here is the nucleophile, your alkyl halide is the electrophile. Okay, good. So similar question here. We've changed our two substrates. Responses. 34. Electrophile. Right. So A is the electrophile, B is nucleophile. So in this case here, we've got a this carbon's got the polarized bond to bromine. So this carbon's the delta plus, bromine's the delta minus. We've got our nucleophile. So carbon with the minus, so connect the dots, negative goes to positive. This will attack on the opposite side and that will leave. So our wedge becomes a dash over here. So we've got inversion of stereochemistry. And our leaving group is the bromide, so it's leaving. Okay, I've got a question for everybody then. If you look at the cyanide ion, we've got carbon with a lone pair and nitrogen with a lone pair. And I've drawn this with the carbon with the lone pair attacking instead of the nitrogen. Why have I chosen carbon instead of nitrogen?
To create a neutral charge.
Okay, right. So if we were to do our product here, if we were to draw it the other way, with nitrogen attacking, we would have this. And formal charge-wise, nitrogen would have a plus, carbon would have a minus with all of our octet stuff. So this product certainly has got, when it comes to formal charges, is neutral. Is there another, that's completely reasonable. Is there another answer? Okay, then there's a couple private little messages saying that of carbon and nitrogen, carbon is less electronegative, so it's less able to stabilize negative charge, so hence it would want to use it to attack. So that's also good. Yeah, so you can actually form these sort of things here. They are quite unstable, but right, so carbon's less electronegative than nitrogen, so it's the more nucleophilic end of that molecule, or that ion, I guess I should say. Okay, good. Excellent. All right, now let's go on to the last one. So this was the third of the three examples I had previously. This is the third one. B is the electrophile, A is the nucleophile. That is indeed correct. Pretty consistent percentage getting those questions correct. Okay, so now this is an example where basically the two types of reagents are in different places here. So H so methyl iodide, this will be the delta plus, iodine's delta minus, lone pair of our nucleophile here, and it is going to attack on the opposite side. The iodide will leave, so it becomes our leaving group. And we formed an ammonium salt here, or an ammonium ion. So nitrogen bonded to 4 alkyl groups. These are, your water softener will have this type of structure in it. So often the alkyl halide is over here and the electrophile is above the arrow, but that's not always the case. Sometimes they're reversed, so just keep that in mind. So The nitrogen's going to donate its lone pairs. We're going to break this carbon iodine bond to form iodide and our product. Okay, good. All right, now the next thing we were going to do is, so there's basically two types of substitution reactions that we're gonna, these nucleophilic substitution reactions, which take place on sp3 hybridized carbons that we're gonna look at. And the second one is a unimolecular reaction, which, I'll move that down there, in which the carbon leaving group bond breaks first. And in doing so, we're going to form a carbocation, and then the nucleophile can attack the carbocation, and then you're going to get your substitution product. So during this type of reaction, the rate determining step is, it only involves the alkyl halide because it's the leaving group which is just departing. So we're going to have to set up this reaction to allow this type of thing to take place. So leaving group leaves, nucleophile attacks, and then we've got our product. So kinetically, if we're to draw the rate equation, the rate's going to be dependent upon some rate constant, which we calculate, but it's only going to be dependent upon the concentration of your alkyl halide, because only the alkyl halide is in the rate determining step. So it doesn't matter if you've got like a high concentration of nucleophile, it's not going to increase the rate at all. So, and that's the difference between like a SN1 and SN2. In an SN2 reaction, you can increase the amount of alkyl halide or the nucleophile, and that's going to increase the rate of the reaction if you're doing experiments on that, measuring it. But in the case of a unimolecular reaction, it's only the alkyl halide because the rate determining step is breaking this bond. The formation of the other bond happens after the rate determining step. So the energy diagram for, I guess I'm getting ahead of myself. So in an SN2 reaction, if you had a chiral center, you got inversion, because the nucleophile had to attack from the opposite side of the leaving group. In the case of a SN1 reaction, though, it's completely different. So if the rate determining step is the departure of your leaving group, what you form is a carbocation. And of course, carbocations are trigonal planar. So they're flat. And if you're a nucleophile, you can attack from side A or you can attack from side B. It's completely, it'll be completely random. So statistically, you're going to get a 50-50 chance of going on either side. So the nucleophile can attack on either side, which means that if you had three different groups or three different R groups on your attached to this carbon, you are going to have these two molecules as your products. And if we look at them like from stereochemistry wise, you will see that they are mirror images of one another and they'll be non-superimposable, which means that this guy, B and A, are going to be enantiomers. So you're going to make 2 enantiomers. And they're going to be a 50-50 mixture of those 2 enantiomers. And so this would be a racemic mixture. So in an SN1 reaction, if you have a chiral center, instead of getting inversion, you get racemization. Which is going to be a really sad thing, right? But it's hard to it's hard to make. Well, unless you're borrowing from nature, which has lots of chiral compounds. But if you take all the effort in the world to make something chiral yourself, and then on one of your next steps, it becomes gets racemized. So you go from pure sort of like R stereocenter to a mixture of R and S. You're going to be sad. It's just one of those things, life of an organic chemist. So if you've got a chiral center, it's going to be racemized. So that's one of the key points here. So stereochemically, SN2 reactions, you get inversion of stereocenter. SN1, you're going to get racemization. All right. Any questions on that? Okay, I'll take that as a no. All right. Yes, this was where I was going first. Okay, so oops. Okay, so the energy diagrams of these 2 reactions couldn't be more different, right? So for an SN1 reaction, because the first step involves the breaking of this carbon X bond, you form a carbocation intermediate, which is way up here. So this is a high energy intermediate. Just think that carbon with a positive charge, carbon doesn't want a positive charge, so that's gonna be a high energy intermediate here. And so there's going to be an activation energy and a transition state to get to the carbocation, and then it's going to quickly react with a nucleophile to form our final product. So there actually be 2 different transition states here. And the rate determining step is the formation of this carbocation. So this peak here will be the highest one in the energy diagram. Now this is quite different from an SN2 reaction where you've just got one transition state. And remember, what that would look like is you are breaking your carbon X bond and you're forming your carbon nucleophile bond, and this thing is going to look like can't isolate it, of course, but this is going to be a sort of trigonal bipyramidal structure where the carbon X bond's breaking and the carbon nucleophile bond is forming. Okay, yes. Now, if I was to ask you, in this rate determining step here, this transition state number 1, should that be early or late? Right, late. This should be a late transition state. Okay, so then it's going to closely resemble the carbocation intermediate, right? So carbon with a positive charge. So this has got a carbon with a delta plus here. So this transition state's going to more closely resemble our carbocation intermediate as opposed to our starting material. And this becomes important for the types of alkyl halides which will undergo SN1 reaction. So the rate determining step transition state is late, so it's going to look like our carbocation intermediate in some way. The SN2 transition state was right in the middle. It's neither late nor early. And so it doesn't resemble anything. It's this trigonal bipyramidal structure. Okay. So now that's good. So that's the key point here, is that because the rate determining step, this transition state's late, it's going to resemble our carbocation intermediate. And we need to know about carbocations to delve further deeper into this type of reaction. I think we discussed them very briefly. Right, so this is what I just basically said. Will the type of carbon influence the rate of an SN1 reaction? Absolutely, yes. The rate determining step is the formation of the carbocation intermediate, right? So this carbocation intermediate is the transition state structure is going to be dependent, it's going to closely resemble this. So we need to look at the stability of carbocations. And what we're going to see is that, remember, I think we did do this before. If we had you had a tertiary carbocation, a secondary, a primary, or a methyl. The most stable carbocation was the tertiary, right? So most stable, least. So, and it basically went in this direction. Okay, so there's a couple reasons why, and this is one we brought up before, which was, okay, so some groups are electron withdrawing groups, like the more electronegative atoms. Some groups push electron density, so electron donating groups, and alkyl groups donate electron density through sigma bonds. So they're electron donor. And so this is an inductive effect. So this is pushing of electrons within sigma bonds. So if you've got more R groups, like a tertiary one, they can push more electron density through that sigma bond to help stabilize that positive charge. So the more R groups, the more inductive effects, the more stable that carbocation is going to be. So on that energy diagram, free energy, where a carbocation will be on this will depend upon the number of R groups. So a tertiary will be lower than a secondary, which will be lower than a primary. Okay, so there's a question in chat. Why do they donate electron density? So when we've got, yeah. Okay, so if we're looking at, so this is basically differences in electronegativity. So we got carbon, nitrogen, oxygen, fluorine, right? So electronegativity is increasing as you go this way. So Carbons, like if carbon's basically bonded to most other molecules, it's like any like nitrogen, all of these, that's all going to be in the tug of war of electron density. It's going to be, they're going to be pulling. So, but when a carbon's bonded to a carbon, the electron sort of the electronegativity difference is less, right? And if this carbon is actually missing electrons because it's got a positive charge, then the other carbons can help compensate that by pushing toward, like donating electrons towards it. Whereas when you've got a little proton, the proton's just got less electron density to donate because there's only 2 in the bond. Carbon's got it's got a lot more. So that's basically so when we're comparing carbon to other atoms, some of them are more electronegative, so they're going to be pulling electron density away, and hydrogen just doesn't have electron density to donate, really. It's got a little bit, but not a whole bunch. We're going to see in a second that carbons have something else going for them that protons don't, and it's going to help stabilize things even further. But alkyl groups are just viewed as electron pushers as opposed to withdrawing groups. And if, in fact, if you take the group theory class, if you construct molecular orbital diagrams on multiple levels, what you can see is that having carbons can increase the level of where electrons are, or decrease it. And so that's a good class to take, just to help view that sort of stuff. Okay, let me clear this stuff out, and let's go to the second reason why the more R groups is going to stabilize a carbocation. So the second factor is what we call hyperconjugation, and hyperconjugation is very similar to a pi bond, in all honesty. So, and what we're doing here is that on the carbons next door to the carbocation, there is going to be a carbon-hydrogen bond which is going to be parallel to this carbocation. So if we were to draw a sort of a Newman projection of this, so the back carbon, let's draw our, so this will be trigonal planar. So so this back carbon here, and on the front carbon, there is going to be one H group that is going to be eclipsing this positive charge. And the electron density, which is in this bond, which is eclipsing, is basically donated through space to help stabilize this positive charge. Sort of like a pi bond, because if we had, like, remember, a pi bond would be 2 p orbitals, and the electron density would be above and below the internuclear axis here. So it's very similar to that. It's not making a pi bond, but it's a very similar sort of stabilizing interaction. So the more alkyl groups you've got, the more opportunities you have to hyperconjugate to stabilize that positive charge. And it doesn't have to be a proton here. This could also be like another R group. This could be, so it's just electron density in this, in a bond, which will be parallel to the to that empty p orbital. If you've got a methyl, you notice that when you've got little protons here, there is no electron density up here, because it's all, they don't have any other, they can't form any more bonds. So there's no electron density above to stabilize through space like this. So there's basically there's two reasons. One is inductive, and basically R groups can donate, and this is through sigma bonds. And the second one is the hyperconjugation, and R groups can donate like a pi bond. So it's one of the protons will line up, so it's parallel to that positive charge, and it will what they call hyperconjugate. So it's a stabilizing interaction. So the moral of the story is, the more R groups you've got, the more stable your carbocation is going to be. And so you could actually draw three different Newman, if you had three different R groups here, you could draw three different Newman projections if you wanted to, showing this sort of hyperconjugation. Okay, any questions on that? Okay. Let's clear all these. So what this means is that so tertiary alkyl halides will generate tertiary carbocations, and these will be more stable. Whereas methyl alkyl halides would generate very high energy methyl carbocation. So you've got, if you're increasing the carbocation stability, you're going to basically be increasing the rate of the SN1 reaction, because that peak on the energy diagram, this transition state, that late transition state, it's going to resemble the carbocation. So if this is more stable, it's going to be lower in energy. And I think the next, this is the next slide basically shows this. So if your starting material is down here, tertiary carbocations are going to be lower in energy, so the rate for these will be faster, and primary are going to be higher in energy. Methyl would be off the chart, so to speak. And so what we have is a complementary system for these substitution reactions. For SN1, the fastest is going to be tertiary. And for SN2, the slowest is going to be tertiary. For SN1, the slowest would be methyl / primary. And for SN2, the fastest is going to be methyl / primary. So it's they're completely, what's fast for one is slow for the other, and what's slow for one is fast for the other. So this is super helpful. Right, so key point, tertiary carbocations are the most stable, so this will be the lowest, which means this activation energy will be the smallest, so the rate will be the fastest. And once you get up here, this isn't going to be competitive. It's going to be way too slow. Something else could happen, i.e. an SN2 reaction. So what we're going to be doing for the rest of the class is there's one type of alkyl halide where both can actually take place. And that's the one where things get quite interesting. Okay, so here we go. So methyl and primary alkyl halides do not undergo SN1 reactions at all. And tertiary undergo SN1 reactions really fast. The ones which are the big unknown, secondary, they undergo SN1 reactions slowly. They undergo SN2 reactions slowly. So it's the secondary alkyl halides which become interesting. Okay, so here are some examples. I should have actually made some questions for this, but anyway. Okay, so in this case here, we have got our nucleophile is water, and this would be our electrophile. So the rate determining step is, so here although I've drawn this with a wedge and a dash, this molecule isn't actually technically chiral because there's a plane of symmetry. So the first step of this will be iodine leaving, and this is going to give us the following carbocation. And so when water attacks this, it can attack from the top or it can attack from the bottom. And so this is why you see these squiggly lines over here. So the squiggly lines means 50% wedge, 50% dash. So this would be a racemate. So all of these here are all racemates. Some of them aren't chiral anyway to start with, but that's what those squiggly lines are actually meaning. Let's just do. Let's just do that. I'm redrawing our little molecule here. Okay, so you notice here the solvent is in fact actually the nucleophile. So that's one interesting thing. Okay, so the first step here, as I drew before, was that our leaving group is going to leave and we're going to form a carbocation. Methyl plus. And then water can come in and attack. So it can attack from the front or it can go backwards. So I'm drawing a little sort of like a dashed line. Either one of those is going to give our product, our next intermediate. And here we go. So there's actually another intermediate in this reaction here before we get to our final product. The last step, all we are doing is we just need to remove one of these protons, right? So another water molecule is just going to come along, and this is purely a proton transfer reaction. It's just going to deprotonate that, and then that's going to give us our final product. And we'll have a little bit of H3O plus in there. So key point is that we're going to form our carbocation. Okay, let's try something. Let's go back a page. No. Okay, so if we were to do this mechanism here, what is the first step? What's the first arrow I'm going to draw? Right, we're going to break the bromine chlorine bond. Okay, so this is going to give us the carbocation plus bromide. Okay, next step. What's the next thing we're going to do? Right, the oxygen on the methanol is going to attack carbocation, good. And it can attack from either direction, so we're going to form a racemate here, okay. What's the last step? Right, we need to remove that proton. So we're going to deprotonate that proton, and we're going to deprotonate this proton with methanol. Why am I using methanol to deprotonate it and say not bromide? Because it's the solvent, right? That's an excellent answer. Okay, it's the solvent. There are the number of extra methanol molecules in there compared to bromide is there's trillions and trillions and God knows how many more. So yeah, so methanol is the second reason is that, right, if you were to use bromide, you would form this. And what do we know about HBr? It's a super strong acid. So this would immediately get deprotonated by methanol anyways. So yeah, so we're going to use methanol as the source of to deprotonate that. So right, so that's basically the mechanism for an SN1 reaction. In this case, we're inverting the sorry, I got the hiccups. We're inverting the stereochemistry at the secondary carbon here. Good, okay, perfect. So the obvious question then becomes, when is it, if we're looking at our reactions, we're going to have some starting material and we're going to have we're going to be making some sort of product. There's going to be some solvent here, and there's going to be another reagent here. But in both of these cases, our reagent's going to be some type of nucleophile, and our other is going to be some sort of alkyl halide, right? So when is it an SN1 reaction and when is an SN2 reaction? So we'll need to do some basic analysis of our what are our reagents that we're talking about here. And the most important factor by far is the alkyl halide. So if it's tertiary, it can only be an SN1 reaction. If it's a methyl or a primary, it can only be an SN2 reaction. So our first decision is going to be, we are going to look at our substrate, our alkyl halide, and see, is it primary, secondary, tertiary, methyl? And our first decision is going to be, okay, if it's primary, well, it has to be SN2. If it's methyl, it has to be SN2. If it's tertiary, it has to be SN1. The only thing which can be both is secondary. So the very first decision we're going to make is just looking at the alkyl halide. So let's see here. Oh no, let's do a. Okay, so. Let's. Okay, so I've drawn a whole bunch of different alkyl halides on the board. So let's see here. If we, this one, is this going to be a SN1, SN, or SN2? Or potentially both? Which one will this one, which one will this one follow? SN2, right, SN2. SN2 because this carbon here is bonded to one other carbon, right? So it's primary. So this guy's primary. So, right, so it has to be SN2. What about this one here? What type of substitution reaction could it go through? Both, right. So here we've got, let me, different color. This is our electrophilic carbon right here. It's bonded to one, two other, so it's a secondary. So secondary could be SN1 or SN2. So it could be both. What about the one I'm surrounding in purple here? SN1. Right, 1, 2, 3 carbons attached to the alkyl, to the electrophilic carbon. So this is a tertiary, which means it has to be SN1. Okay. What about this one over here in red? Okay, so the one over here in red, this one is, and actually this one here, they're both the same. So the problem with both of these is that this carbon here or here is sp2 hybridized. So these don't, if it's sp2 hybridized, these won't undergo SN1 or SN2 reactions, because for SN1 and SN2, the carbon, our electrophilic carbon, has to be sp3 hybridized. So it has to be no double bonds. So these types of molecules can undergo substitution reactions, but it's a completely different mechanism. And quite often they're mediated by a whole bunch of other sort of fancy reagents, transition metals, and that sort of stuff. So our SN1 and SN2 are only for sp3 hybridized carbons. So keep that in mind. These would be non-reactive to substitution reactions that we're going over. Okay, good. All right, now, well, let's see here. Okay, so if we've got a primary alkyl halide, it's got to be SN2. It's got a tertiary, has to be SN1. But in the case of secondary alkyl halides, we have to do further analysis to determine which mechanism is going to occur. And so there are a couple of factors that are really important. So we're going to go through them all. One will be the nucleophile. Another one will be the leaving group. And an important, super important one is going to be the temperature and the reaction conditions. And the solvent is going to be critical for this. The solvent's really going to play a major role. Of these three factors, the one which is the least important is really the leaving group, in all honesty. But we do talk about the leaving group so everyone can recognize what is a good leaving group and what isn't a good leaving group. So that's what we're going to talk about. So the nucleophile is going to be super important, and the reaction conditions. Okay, so why is the nucleophile is important? Because if you look at the two rate determining steps, so in the SN2 reaction, remember the two molecules had to collide with one another, and so the rate was dependent upon both the alkyl halide and the nucleophile, because the nucleophile was attacking that carbon with the leaving group, and then the leaving group was leaving. So the rate was dependent on the nucleophile and the alkyl halide. In an SN1 reaction, conversely, the rate determining step was just the leaving group taking off. And so in the rate equation, it's only dependent upon the alkyl halide. The nucleophile isn't involved at all. So one way that you can promote an SN2 reaction over the possibility of an SN1 reaction is to make sure that you've got a good nucleophile in your reaction. And if you want to boost the concentration of it, that's only going to help. It's only going to increase the rate. So an SN2 reaction is going to be promoted by using a good nucleophile. Whereas an SN1 reaction is going to be promoted if you use an extremely poor nucleophile. So, because it's not involved in the rate determining step. If you've got a really good nucleophile, and you're trying to do an SN1 reaction for whatever reason, and we're only talking about secondary alkyl halides here. You want to use a poor nucleophile to promote an SN1 reaction, whereas you're going to want to use a strong nucleophile to promote an SN2 reaction. Because the nucleophile is in the rate determining step for an SN2, but it's completely absent from the rate determining step in an SN1. So, but I've sort of erased, or underneath this in green, the next question is, what makes something a strong nucleophile or a good nucleophile? So what makes something a strong nucleophile? So at the very start of the term, we went through a whole process of determining what was a strong acid, what was a strong base. So this is basically going to come back to what we were talking about there. So generally, nucleophilicity, I'll use my laser here. It's funny, in Zoom, there's all these little sidebar things. I'm trying to get them out of the way here. So it's lucky that we remember base strength from our acid-base sections. That's a good thing. So remember, nucleophilicity is generally going to parallel basicity. So strong bases are typically strong nucleophiles. So if we had hydroxide versus the acetate anion versus water, the strongest base of these would be the hydroxide. And why is hydroxide a stronger base than, say, this acetate anion or the carboxylate? Why is hydroxide a stronger base? Right. So in this anion here is stabilized by resonance, right? You can move these electrons here and move those electrons up. So this anion is resonance stabilized. This oxygen isn't stabilized at all, except for through electronegativity, but so is this. So this is stabilized by resonance. This one isn't. So this negative charge is going to be more reactive than this negative charge, right? So okay, good. Now, why would hydroxide be a stronger base than just plain water? So hydroxide's got a charge. So when it grabs a proton, it's going to form a neutral molecule, water. Whereas when water grabs a proton, it's going to form a charged species, the H3O plus, right? So whenever you've got an atom which has got a formal charge of minus compared to something which to its protonated, so the conjugate acid of it, the base is going to be a stronger base than the conjugate acid, right? That's just one of those sort of things. So we basically did all of this when we were talking about when we were doing our acid-base stuff. The second arrow here, right to left across the periodic table, this is exactly what we did before as well. Carbon is less electronegative than nitrogen, so it's less able to stabilize this negative charge, so it is more basic. And it's also going to be a better nucleophile too. So this is just the same trend we had before. And I got ahead of myself. So the anion versus its conjugate acid. So the base is always going to be stronger than its conjugate acid. So S minus is going to be more nucleophilic than just H2S, or hydroxide is going to be more nucleophilic than H2O. So all of these, the first 3 points is what we did during the very start of the term. The part which is slightly the new part, let me move this up here, is that polarizable atoms make excellent nucleophiles. My screen, I gotta get this, it's a bit low on my screen. I don't know, I wanna hide that. No. There's a little bar at the bottom, so I can't actually see what my polarizable atoms make excellent nucleophiles. But if we're thinking about polarizable atoms, remember they're lower on the periodic table. So things like I minus, Br minus, sulfur, things that are polarizable make excellent nucleophiles. Now, the difference is I minus is a horrible base, right? Because it can stabilize that negative charge through its large atomic size. So this is the one place where basicity and nucleophilicity completely diverge. And so polarizable atoms can be excellent nucleophiles, but they're the weakest bases you can imagine. So that's the one difference. So I minus, we're going to see I minus being used as a nucleophile, but it's not a base at all. So that's the first point. So now solvents do play a real important role in this, in point number 4. So there's certain trends that can be reversed by choosing different solvents. We'll get into that a little bit later on. So generally, when it comes to being a nucleophile, you can just think of it, is this a good base or not? And it's going to typically work, except for the polarizable part. So things that are lower on the periodic table, iodine, bromine, sulfur, because it's lower than oxygen. So, and it's more polarizable. Okay, so I have, oops, that's wrong. Oh, and this was, yeah, we're about to run out of time, but this was the general reaction here, just to show this. So somebody ran an experiment and they used methyl bromide as their alkyl halide, and they changed the nucleophile, kept the reaction conditions the same, just to test and measure the rate of the reaction, just to see how the rate would increase with changing the. So the nice thing about the methyl halide is this one is it's going to do an SN2 reaction all the time. So water, it's got a rate of 1, and everything else you'll notice is increasing from that rate of 1. So the acetate anion, the carboxylate anion increases the rate 500. NH3, 700. Remember, nitrogen's less electronegative than water, so it's more likely to donate its lone pairs, and the rate goes up 700. Chloride, 1,000 times faster. Hydroxide, so this isn't stabilized by resonance like here. The rate's now 16,000 times faster. Methoxide, 25,000 times more reactive. And you can think here, comparing like hydroxide to methoxide, you got a methyl group which could push electron density, which would make this oxygen even more nucleophilic. This is sort of an example of that, how methyl groups or alkyl groups donate electron density. So if this is pushing lots of electron density towards this oxygen as a donator, it's going to make this even more reactive. And then here we've got our polarizable atoms, iodine, sulfur, super nucleophilic, carbon with a minus, cyanide, super nucleophilic. So this is just a little demonstration of just how the nucleophilicity increases. So if you're using something that's a strong nucleophile, it's going to increase the chances of a SN2 reaction. If we go back a whole bunch of slides, you remember the two examples we did the mechanisms for? One was using water for the SN1. One was using water as the nucleophile. The other one was using methanol as a nucleophile. So both weak. This would probably be slightly faster than one, but it's going to be a really weak nucleophile. So SN1, we're going to want to use weak nucleophiles. In SN2s, we're going to want to use strong nucleophiles. I think my time is basically up. So we'll continue on this part on Tuesday. And I guess I've got lots of questions I can think of asking with regard to the start of class. So that's going to be good. Were there any questions at all? You know, the horrifying thing is there's only now, after today, there's only 3 classes left in the term. It's like, where did time go? But anyway, any questions at all? I'll send you an email about that question. All right. So if there aren't any questions, will we be able to have a review session before the exam? I sure hope so. Okay. Yeah, well, I sure hope so. Okay, so I guess what we will do is I'll see everybody on, what day is it? Thursday today? I'll see everybody on Tuesday. And what am I doing? You bet. I'm trying to stop something. Stop recording.